start. It is a real pleasure to introduce the speaker today. Everyone wonders if that's my brother. Huh? No. He's older brother, though, but I was told that I look wider. He got his PhD from University of Chicago in 1997. Then he moved as a postdoc to MIT and spent there 2 years, right, 2 years in MIT, and then moved to Stony Brook, and now and since then he's been in there, and for the last 4 years he's been a deputy director of the Simon Center for Geometry and Physics. The logo is over there. And for his career, he's been interested in different topological and thermodynamical description of different quantum systems, such as superconductivity, quantum Hall effect, and so forth. And today he's going to talk about that exactly, the chiral quantum fluids and related problems. So here's the speaker. Yes. And there is one more thing I need to present you from our department. The gift.
Amazing.
It has your name on it.
Okay. Can I use it right now?
Right. Let me put better.
Okay. Okay. Thank you very much. It's a pleasure to be here. I'm here not the first time. I think it's the second one, and one of the reasons of why this is great to be here is because Artem gives me nice introductions. I don't remember that in our teenage years. Okay. So the topic of the talk is odd flows, and the odd is both has meaning of strange and odd in terms of the number theory or odd number, and you will see why. This is probably the joke which Yossi Avron invented at some point, but I can only speculate. And let me start with reading some paragraph from this paper, Perfect Fluid Theory and its Extensions, by those authors. And the paragraph is that the dynamics of fluids is described by classical field theory, whose origins lie in the 19th century, like Maxwell's electrodynamics, with which it shares some antecedents. The electromagnetic theory has enjoyed much development. It passed into quantum physics, and the resulting quantum electrodynamics served as a model for its non-abelian generalization, Young-Mills theory, which today is at the center of a quantum field theoretical description of fundamental physics. We believe that fluid dynamics can undergo a similar evolution and play a similar generative role in physics. So I share this opinion of others and think that hydrodynamics is the science of 21st century. And indeed, it's now developing pretty quickly, both in relativistic physics and in non-relativistic physics of quantum and classical systems. So why is this so? Why is hydrodynamic description so powerful and interesting? First of all, it's description in terms of directly observable quantities. Well, this is a little bit more subtle than that. So there are also a lot of quantities which are not directly observable, but at least when you talk about flow of mass and flow of momentum, these are directly observable quantities. It's universal. It's based on conservation laws, and that's why it can be applied to many very different systems. It works for strongly interacting systems. Actually, in fact, in many cases, it works better for strongly interacting systems than for weakly interacting systems. It can easily describe linear response. You just linearize hydrodynamic equations and get your linear response. But also describes a lot of nonlinear effects, such as vortices, shock waves, turbulence, etc. Of course, it's impossible to talk about hydrodynamics as a whole. It's just one colloquium talk. So I'm going to talk about hydrodynamics of chiral fluids, and even will be more specific, so I will describe more in a second. So the outline is the following. First, I will say what chiral fluids are and what I mean by chiral fluids. And I will talk about fractional quantum Hall effect and linear responses of fractional quantum Hall effect. It's my main motivation, but in this particular talk, I will not go into much more detail. The main part will be here when we discuss fluids with odd viscosity. So this is the main hero of this talk. And we will talk about systems of active rotors and manifestations of odd viscosity in systems of active rotors. And please interrupt me with questions. I'm not sure because it's a custom here, but it will be useful. So chiral fluids. So this is the citation from Lord Kelvin, 1893. He was probably the first one who used the word chiral. I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. And the word chirality itself is derived from the Greek chair, which is hand, a familiar chiral object which cannot coincide with the left hand no matter what you do. And in this particular talk, we will refer to systems as chiral if the parity symmetry is broken, is explicitly or spontaneously. And what are the sources of chirality? First of all, you can have chiral constituents. Many molecules, chemical molecules, have chiral nature. So if you put together those right spiral molecules, the resulting theory breaks parity, and it might have some interesting effects associated with that. External magnetic field breaks chirality. So for quantum Hall effect, it's natural that parity is broken, and you expect some effects related to that. There are also liquids or systems where there are some rotations in a definite sense, in definite direction. For example, if you have a lot of tops rotating counterclockwise or clockwise, altogether this system is a chiral system and might expect some interesting properties from that. And also, more subtle, there are some intrinsic angular momentum or spin. For example, particles with, which spin is oriented in one particular direction, also chiral system. In this particular cases, you have to make sure that there is some exchange between the spin and orbital motion of the particles, otherwise they're totally decoupled. So let me start with one system, which is just a funny system. So it's kind of nice to show this. So this is the last part of my talk will be actually stimulated by this paper of 2005, where authors were inspired by the toy called Rattleback, and they basically created similar things which breaks parity using some pieces of wire, and then created some gas of those wires. Let me explain this picture later, but let me show you just what Rattleback is. So what I'm going to do is I'm going to show the movie, and then I will simultaneously pass the toy. So this toy is known since ancient times, and it can freely rotate in one direction, but if you rotate it in the other direction, it stops. So it was the original one, and rotates in other ones. The parity is obviously broken here. If you tap this toy, it starts rotating in a very particular direction. And now take a close look at what happens. Actually, it rotates in the wrong direction, then starts vibrating, and then changes rotation to the opposite one. So this is a typical example of the system which has inherently broken parity, because chiral constituents have broken parity. And what the authors of this paper did is that they put a lot of such systems on a support. They started to vibrate this support with some frequency, and then they basically recorded the motion. So here, the circle means the initial position of this small thing, and this is the trajectory over some time. And what you can see is that you can obviously see that there is a chiral edge current, for example, here. So these particles move counterclockwise on the edge, but more or less randomly in the middle. So this is one of the effects of broken parity in the system. And the question which we are going to ask is it possible, and they asked also as well, is it possible to describe hydrodynamically this kind of system collected out of parity broken systems? Not necessarily. So you mean constituents or the whole system itself? The constituents here, they're not plane. You can see that it goes like this, and then it goes out of the plane. So they were optimizing Kangol and doing a lot of stuff in this work. So basically, if you take these rattlebacks and shake them, they will start moving in a similar way. And there are many other systems. I will talk about a few other experimental systems. More or less stable by default, yes. You can do it at home. Right. So chiral systems, what are known chiral systems? I'm pretty sure there are more known chiral systems. This is like which I know, right? Plasma in magnetic field. So the part of those parity breaking responses are listed in Landau-Lifshitz volume 10, some page if you know the page, plasma in magnetic field kinetic theory. Obviously, superfluid helium-3A has non-zero intrinsic angular momentum, so it in principle violates parity. But it's all three-dimensional systems. typically. So what I'm going to do is talk about two-dimensional chiral fluids in this talk. So some example which is relevant is fluids made out of vortices. So you can think about two-dimensional film with vortices, and you ask what's the effective dynamics of these vortices if they are of the same circulation, if you look at the scales, which is much bigger than intervortex distance. They have the same circulation of the same sign. Yeah, so we need parity breaking. And you can find some interesting consequences of this. So I'm not going to talk about this, but I'm going to talk about quantum Hall effect and systems of active rotors, which can be realized in many ways, like colloids in rotating magnetic field is one example, fluids made out of spinning tops, another one, etc., etc. So I will mostly talk about these two systems. And the main question we are going to ask when talking about the systems is, what are the consequences of chirality on the fluid dynamics? And there are many, so I'm going to concentrate on what's called odd viscosity. So fractional quantum Hall effect. I refuse to think that there is anybody in the world who does not know about fractional quantum Hall effect, but still I will make this introduction, which is like 10-slide introduction, and then we'll describe quickly my motivation coming from fractional quantum Hall effect. So fractional quantum Hall effect, integer quantum Hall effect was discovered in 1980 by von Klitzing, and in 1982, the fractional analog of quantum Hall effect was discovered by Tsui and Gossard, and then Laughlin made an important step of making the theory of the Hall of fractional quantum Hall effect. So it was immediately recognized that this is a huge discovery, and I think this is one of the most fascinating discoveries of the 20th century. So for example, Nobel Prize for integer Hall effect was discovered just 5 years later than the discovery itself. That's very rare. So classical Hall effect is the following effect. So we take some semiconductor or metal or anything, apply magnetic field perpendicular to some particular plane, apply voltage across the plane and measure current along the plane, and divide voltage by current, and that's quantity is called Hall resistance. So if you take elementary kinetic theory of resistivity, then the Hall resistance, which is here is in red, should be linear function of magnetic field, because the reason for this Hall effect is a Lorentz force, which is proportional to magnetic field. So this is what you expect from classical Hall effect, which was discovered by Edwin Hall in 1879. And longitudinal resistance is supposed to be more or less constant, not depending on the magnetic field. Okay. So now the question we ask is, what will happen if we put this sample, first of all, make it two-dimensional, which is made by confining electrons to the surface of semiconductor. Then we'll make very clean samples with very high mobility, make very low temperatures, lower than 1 Kelvin, or for fractional quantum Hall effect, it's even millikelvins, and put it in a strong magnetic field perpendicular to the two-dimensional surface. Typical magnetic fields are of the order of 10 Tesla in these experiments. And this is what happens. This is a plot. So just here for reference, this was what expected classically, the red line here. And now what happens here with all these plateaus, which are called quantum Hall effect plateaus. And instead of this straight line, you will have this type of oscillations. And you notice that whenever you have plateau in Hall resistivity, you will have dip in the regular resistance. So it's like insulator. So what happens is that there are plateaus developed in some particular values of Rxy. Moreover, if you calculate the values at which these plateaus occur, they are measured in integer number times h divided by e squared, where h is a Planck constant and e is electric charge. Each h over e squared is made out of two fundamental constants, electric charge of electron and Planck constant, and this has a unit of ohms. So this is a unit of resistance. And it turns out that coefficient of proportionality for where this plateau is developed is exactly integer, and that was discovered in 1980. And then if you put it in even stronger magnetic fields and even cleaner samples, etc., you'll see that additional plateaus are developed where the coefficient in conductivity is 1/3, and this is called fractional quantum Hall effect. And there are many plateaus at very different tempos. The most amazing thing about this quantum Hall effect is that the accuracy with which this plateau is exactly h over e squared is 1 in a billion, so 10 to the minus 9, which is quite amazing because there are impurities, and this is the solid-state systems, and you can measure fundamental units with such an accuracy right out of that. So now this effect is put in the base of the standard for resistivity, actually. Okay, so skipping all the development, all arguments, I will just say that fractional quantum Hall effect can be thought about as an exotic fluid. And the new type of quantum fluid is a citation directly from the Nobel Prize for the fractional quantum Hall effect. And it can be thought about as some kind of quantum condensation of electrons coupled to vortices of this fluid. The quasi-particles in this state are gapped, have fractional charge, like 1/3 is a typical example, and fractional statistics. And fluid is ideal, there is no dissipation. There is a density-vorticity relation of a very peculiar type. So whenever you try to rotate this fluid, you will see increase of density of electrons, and vice versa. If you try to increase density, fluid starts rotating. And there are interesting transverse transport properties. The Hall conductivity is a fingerprint of Hall effect. It's quantized, as you saw, with exact values given by fundamental constants. But also there is a Hall viscosity and thermal Hall effect, which importance was recognized relatively recently, and I will talk about them. And there is also chiral dynamics at the boundary of the system, but I will not talk about this at all in this talk. So there are some chiral H currents. This viscosity is not dissipative. I will talk about this in a second. Actually, right here I start. So Hall conductivity is a quantized and robust signature of fractional quantum Hall effect. If I apply electric field in x direction, I will see current in the y direction, and proportionality coefficient is measured in units of e² of h, where nu is the exact rational number for fractional Hall effect or integer number for integer quantum Hall effect. And the question is, are there any universal transport coefficient, or this is the only characteristic of the state? And it turns out there is Hall viscosity, which is related to transverse momentum transport, and there is thermal Hall conductivity, which is related to transverse energy or heat transport. So heat transport in direction perpendicular to gradient of temperature, and I will talk about Hall viscosity next slide. So the question which occurs is how to calculate those corresponding transport coefficients corresponding to these two quantities, what are results for different Hall states. It does. Yeah, it also is an integer Hall effect. Yeah, it does. So Hall viscosity. So the regular viscosity, which is also known as shear viscosity, is the following thing. If you take a gradient of velocity, gradient of x velocity in y direction, then the layers of the fluid have mutual friction, and this results into the forces in the direction opposite to velocity, which decreases the gradient of the velocity. And because the forces are against velocity, so there is a dissipation of energy, and basically it's this effect kind of opposes to gradients. And however, if parity is broken, then you have another possibility. If you have a gradient of velocity in the same way as here, you can have additional forces appearing in the direction perpendicular to the velocity. So notice here that you have to make a choice whether this force looks down or up. And that is possible only because you have parity breaking. If you don't have that, you don't know where to put your force. So in this particular case, of course, the force is perpendicular to velocity, so there is no work done and no dissipation in particular. So this is dissipation-less transport. So it's usually some problem with terminology, of course, because usually people used to viscosity as something dissipative, right? It's what first comes in mind. But technically, this is a part of viscous tensor, which is a tensor of the force rank in the dynamic equations, and part of it is given by this coefficient if parity is broken and it's allowed. And Avram Zeiler-Nogrov asked the question, what will be this coefficient in quantum Hall effect, and calculated it for integer quantum Hall effect states. And then it was developed into fractional Hall effect calculations. So how do we calculate this coefficient? Actually, the technique is quite interesting. So we basically put the quantum Hall system in some interesting external geometry. So we think about quantum Hall effect on the surface of some curved, on some curved surface. And we ask what currents will flow if you deform the surface in some particular way. And of course, this metric is not necessarily the metric which you have in the vicinity of black hole or anything. This actually simulates some elastic deformation of the crystal. So from solid state physics point of view, you should think about the surface as a way to apply strains to your crystal. So we're talking about elastic responses here. So generally, we put it in the variable magnetic and electric fields and geometry and measure electric currents and stresses, and this will give us a lot of different responses. Now, this is slightly technical, so I will just go over it just to show how one can encode this compactly. So the idea is the following. We have quantum Hall system, which is electrons in Landau levels, forming fractional quantum Hall effect. The quasi-particles are gapped. So let me integrate out electrons. Let me average over the motion of electrons and ask what will be currents flowing in the system as a function of applied electric magnetic fields and deformations of the surface. And these linear responses can be effectively and compactly encoded into this effective induced action, which is obtained by calculating path integral. And there are just three coefficients in front of those geometric terms. This term is a topological term known as a Chern-Simons term. You've probably heard of this. And this is called Van Z term, and this is second Van Z term in this context, or sometimes gravitational Chern-Simons term. And coefficients here characterize Hall state, not uniquely, but for any quantum Hall state, you can ask what the values of those coefficients. And the first coefficient gives you the Hall conductivity. This multiplied by this gives you Hall viscosity. This multiplied by this is related to thermal Hall transport. So this is the compact way of doing this. This omega is a spin connection, so d omega is a curvature of the surface in particular. I'm not going to in detail. So the question is how to calculate this for quantum Hall systems, and it was done. So I'm shamelessly promote my former student Andrei Gromov, who is now a postdoc in Chicago, in Kadanoff Center. So in this particular paper, you will find all necessary references and also computations for many types of states of all this quantities. So there are various techniques used there. So I'm not going to talk about this, but in particular for Laughlin state, for states with 1/3, 1/5 Hall conductivities, you will have these values of the coefficients written on the previous slide. There are many other works, of course, and I'll just refer you to reference. The C. So the C is some coefficient in front of this thermal Hall, and it's related to the chiral charge of the boundary theory. So this is central charge of the boundary. Okay, just to tell you how beautiful this work by Avram Zeiler and Zograff is let me describe this. This is a different way to approach the computation of this Hall viscosity, and this will be the last quantum mechanical slide in this talk, I think. So you might have heard about Laughlin's argument for quantum Hall effect, which goes as following. So let's suppose that I have a torus, and my quantum Hall effect is on surface of this torus with magnetic field perpendicular to the surface of the torus at all points. And let me assume that in addition, I put thin solenoids with magnetic flux confined into the solenoids, one in this hole of the torus and another in the inside of the torus. Then what I can do, I can, for example, change the magnetic flux inside this red solenoid. As a result, the electric field will be induced in this direction. As a result, current will flow in this direction. And you can ask what's the motion of the charge when you change the value of the flux here. Or you can take a wave function of the ground state system and ask how wave function of the ground state changes when you change this flux of the solenoid. Because it's quantum mechanics, this flux is observable. It changes the ground state wave function, unlike in classical system where all magnetic field is confined here, all charges move here, so this is not observable. So you can change this value nx of the flux through this hole. You can change the value of ny flux through this hole. You can make the space of the parameters nx and ny, and you can just take your wave function and change its fluxes in such a way that come back to the original point. The question is, will there be any total flux phase change of the wave function? And it turns out that there is. It's called Berry phase in general context. And in this particular case, this phase will be proportional to the area of this loop. And coefficient of proportionality is Hall conductivity. So I'm not explaining this. This is called theory of adiabatic transport, but this is how beautiful it is. Or instead of measuring some particular things. You just take system in the ground state, you study how the phase of this wave function depends on the parameters of the space, and as a result, you extract Hall conductivity. Okay. So now what Avron, Zayler, and Zograf did is they said that, okay, there are more parameters to change. So let's put quantum Hall effect on torus, of which we will think as parallelogram with identified opposite edges. So we glue this edge to this edge, we glue this edge to this edge, we'll get parallelogram, which is characterized by this complex number tau, or coordinates tau x and tau y of this edge of the parallelogram. I take this one to be 1. So the question is now, let me suppose that I deform this parallelogram in such a way that I come back to original point, changing on a way tau x and tau y. So the tau y, tau x is described like a strain. So when I have parallelogram which is skewed, it's like torus which was deformed this way, and then when I change it like this, it means that I take torus and make some strain in this torus, in some closed loop, which is described by this. So I'm not sure whether I described physical meaning, but it's basically how the, if I do it with finite speed, I will see that I actually impose some particular velocity of the surface at every point corresponding to the gradients of velocity as a strain. But this is geometry, and I ask how fluid moves on top of this. So I deform the torus itself and ask how fluid moves. Yeah. So what you do technically, you just take ground state wave function of quantum Hall effect on this parallelogram with periodic boundary conditions. Well, they're not quite periodic, they're quasi-periodic because there is magnetic field perpendicular to parallelogram, but it's known how to impose those conditions which are periodic up to phase. And you do it, and then you change this parameter.
In this case, I understand that.
Oh, so this, you're talking about the periodicity in changing flux by 1. You change the flux by 1. I did not use this periodicity even here,
Yeah,
right?
I understand, but otherwise you wouldn't have topological.
No. So there are two things here. When I did this small closed loop, I never used the fact that ground state is periodic with respect to phi.
But it is on the closed
Yeah.
surface, topologically.
Oh, this is also closed surface.
Why it is closed?
So this I draw it this way, but what I mean is that when particle goes here, it will reappear from here. So I glue this edge to this edge, and I glue this edge to this edge. So I get torus. So topologically it's torus. But I want to show that if I put some coordinates here, that the coordinates will be skewed.
You should identify, to say 0 and 1.
Okay. So let's imagine. Let's take this parallel. Let's take this and glue it to this edge. Just do it like this.
Sure, yeah.
I will get cylinder, and then I'll take this edge, which will be circle, and identify it with this edge. I'll get torus. No, I don't have a piece of paper. Otherwise, I would just.
No, it's what you are doing. Numerically, I understand. What does it mean?
So topologically, it's absolutely the same. I get torus. But I have some additional parameter which is tau, which is what tells me what complex structure is. So in 2 dimensions there is a complex variable x plus iy. That's a square. If I think of my complex variable z as x plus tau y, I tau y or tau y, that's what is described. So I basically skew some boundary conditions in some particular way and ask if I do closed loop in these parameters, what will be the change of the phase of the wave function? This is closed loop. So I just change this parallelogram and come back to original one. And the question is, what will be the phase? The phase turns out to be proportional to this area also. That area calculated in hyperbolic metric. So it's but basically area. And coefficient of proportionality is called viscosity. So that's what these guys showed. And they use this exercise because they knew exact ground state wave function of non-interacting electrons in magnetic field. They use this exercise to actually calculate it for integer Hall effect. It's more difficult for fractional quantum Hall effect, but because wave function for Laughlin state at least was known on torus, then we could do that, and people did that, like Nick Reed did that and calculated it and computed those coefficients for simplest fractional quantum Polyvac pictures. Okay, so this is like a mixture of quantum mechanics, and we extract some quantity which looks like classical quantity because it's basically viscosity of some type. The value of this also contains some h bar. So it's actually the value itself is proportional to some quantum units. But we can ask the question, what will happen if I now take such a general two-dimensional classical fluid with non-zero nu h, with non-zero Hall viscosity? What will be the actual physical properties? Maybe this will help us to find some observable consequences of this quantity in Hall effect. I have to say that although it was calculated for many, many states, it was not measured yet. So it's still a proposal. So, and we come to the next part, which is fluids with odd viscosity, and this is a recent paper, very recent, it should appear tomorrow on arXiv with the postdoc at the Simon Center, Sriram Ganeshan. And this part is totally not about quantum Hall fluids. What I'm going to do is I'm going to borrow that concept of this new age and ask what will be the physical consequences of non-zero Hall or odd viscosity for the motion of two-dimensional fluids, in particular incompressible fluids in this case. So this probably will give you the way to fill this. Actually, this goes along with the project which was started by Avram himself, who a couple of years later, after they did it for quantum Hall effect, basically formulated the question. He said that one time reversal is broken, the viscosity tensor have non-vanishing odd part. And that paper was called odd viscosity. And in 2 dimensions, and only in 2 dimensions, such odd viscosity is compatible with isotropy. So this is a big difference. In helium-3A, you also expect some odd components of viscosity tensor, but it's typical 3-dimensional system, and as far as I know, nobody studied it in helium-A films, which may be similar to this. So there, to make this antisymmetric tensor into indices, you need some special direction, which is usual direction of magnetic field in plasma, or you need some additional direction, which is special in some way. In 2-dimensional system, you do not need additional direction. It's sort of direction perpendicular to a 2-dimensional plane. And what Avram is saying is basically, so let's solve Navier-Stokes equation with odd viscosity term added and see what are the consequences. And he found first consequences that there are particular type of circularly polarized viscosity waves. You can make a shear, and then the shear will propagate through the fluid. And it's the polarization, the shear parameter will be actually rotating, so it's like circularly polarized. No damping. So you can add damping if you assume that it's smaller than everything else, but the odd viscosity itself does not require any damping. It can be described in totally dissipationless formulas. So he found this dispersion relation for this viscosity waves. He also found a simple interpretation of odd viscosity. So if you have a disk rotating, then there will be additional pressure on the disk, which is similar to the pictures which I show here. Okay?
Yes, you mean that when compressed?
Right. Compressed or strained, depending on the sign of odd viscosity or the sign of your parity breaking. There is a sign. So it can be both directions. So unlike the regular viscosity, which would be positive.
Now, when this sign changes?
For example, in Hall effect, if you have magnetic field this way and rotate it this way, it will be compressed. But if you have magnetic field this way but rotate the same way, it will be strained. So it depends on the sign of parity breaking. And again, the shear viscosity should be positive because of second law of thermodynamics, but this one is not restricted, it's dissipationless. Okay, so let's fix hydrodynamic equations. Let me start with regular hydrodynamic equations just to refresh your memory, and hydrodynamics for students, hydrodynamics is not very often taught now. So basically this is conservation of mass or continuity equation. So we basically say that the derivative of density with respect to time, if you sit on the particle, can only come from the divergence of velocity. This is the material derivative, this big D. And the same equation for momentum, which is mass density times velocity. This is momentum density. The momentum density can change only if there are intrinsic forces which are described by stress tensor sigma acting on the system. So, and sigma usually is written as pressure term which is isotropic, plus some term which depends on gradients of velocity, which is called viscous part of the stress tensor. This is Landau-Lucius volume 6. Okay, incompressible fluid. I'm going to concentrate in this part only on incompressible fluid. So divergence V equals 0, then you don't need continuity equations anymore. Density does not change. So let's be more specific. Let's assume the density is 1 everywhere at initial time, then it will be 1 everywhere in future. Although this is not necessary for incompressibility. You can have initial density which will just moving with fluid. That's also incompressible. And this is a typical way we write the regular shear viscosity. These are derivatives in direction I of the component of velocity in direction j. Oh, I should put V here, not U, Vj, Vi. I mix U and V. So U and V is the same thing, it's velocity. So, and Navier-Stokes equation is a familiar equation of this type. If you just substitute this in the equations on the previous page and use this, you'll get this. So you have basically that velocity is conserved, changed only by Newton's law by gradient of pressure, but also there is a friction between different layers of fluid, which is, this is Laplacian of velocity. That's Navier-Stokes equation. So if parity is broken, you can add this term, which looks very much like this one, but a little bit different. There are stars here, and the star is rotating by 90 degrees clockwise. So like if I have vector u, and u star means the same vector rotated 90 degrees clockwise. In terms of components, this is what it is. That x component of star vector is y component of the same vector, and y component is minus x component. This uses epsilon ij, which uses a notion of right and left. So this term is only possible when parity is broken. Okay? And if you again just use this substituted in this conservation momentum, you get this modified Navier-Stokes equation, where there is additional term here, which is the Laplacian, but not of velocity itself, but velocity rotated by 90 degrees. And the coefficient is known as odd viscosity. Okay, now, this is general. This is the equation which Avron solved in his paper for compressible case as well. In incompressible case, you can simplify this. Also, Avron noticed that you can absorb this term into combination with pressure. This is not very obvious, but it's very simple calculation.
V and U is the same?
Yes, V and U is totally the same. Right, so I should write on here that identity that V equals U. So sorry about that, it's just, okay. So if I use incompressibility condition, I can put this term as correction to pressure. So new pressure now is P minus vorticity multiplied by odd viscosity coefficient. This is identity. If I use this, I can just show from this that this follows. All right. This is important part because it shows you that if you look at this equation, it looks like Navier-Stokes equation, but with just slightly modified pressure. Okay. Yes, right. So I actually don't even think about the film when I'm writing this equation. I'm thinking about just like having two-dimensional world. And in this two-dimensional world, it's known what's clockwise, what's counterclockwise. Parity is broken. And that's nu zero is constant. Let's take it constant.
When you take this gradient of PQ,
Yes.
then you have the second term, which is gradient of curve.
Does work like this. This is not in 3 dimensions. In 3 dimensions, it would be 0.
Yeah.
But in 2 dimensions, this is just number. So it doesn't work like this. But if you interchange these guys and use incompressibility, you will see that it works.
So what curve is simply this Z.
Right, it's Z component of this. So I'm writing this as if it's vector, but it's actually Z component of this. And Z component means, it's basically dx Vy minus dy Vx. That would be a better way to put it. So I don't know what Z is, but this is dx Vy minus dy Vx. Okay, so let me now move ahead. And let me take curl of this equation. Okay? 2-dimensional curl, so it's all 2-dimensional. Then gradient disappears. And I have an equation for vorticity which can be written this way. And this is absolutely identical to the one which you obtain from regular Navier-Stokes equation without odd viscosity. So equation for vorticity does not know anything about odd viscosity. The incompressibility condition does not know anything about odd viscosity. And there are only 2 unknown components of velocity, Vx and Vy. And there are 2 equations. So I can, in principle, solve these equations without knowing about odd viscosity. So the question is odd viscosity observable at all? So the question is flow independent of odd viscosity, or it does depend on this? And that, of course, depends on boundary conditions. So hydrodynamics is mostly about boundary conditions and about solving bulk equations, although people probably won't agree with this. But so what we can do is we can more exactly formulate the following three statements in the question when boundary conditions depend only on flow, only on velocity. Example of such is no-slip boundary condition. So if I say that there is an obstacle, then velocity at the surface of the obstacle is 0. This is called no-slip boundary condition. And what I can do is I can basically already derive that. I can say that the flow does not depend on the value of odd viscosity in this case. The flow means velocity field does not depend. If I solve problem without odd viscosity, I turn on odd viscosity, flow means velocity does not change at all. The net force acting on the closed contour, this requires some small calculation, but you can show that it does not depend on the value of odd viscosity. The force itself locally does depend on odd viscosity, because remember, stress tensor had odd viscosity explicitly. So if I found the flow with odd viscosity and without odd viscosity, flow is the same, but local pressure, local force on the boundary is different. But if you integrate over a closed surface, it turns out that all differences go away. So the net force acting on the closed contour should be the same. And finally, you can ask what is the net torque on the closed contour. And it turns out that it's not 0 anymore. Even if you just have shear viscosity, you'll have already torques. But what happens that the part which depends on viscosity is given by a very simple formula. It's proportional to the rate of the change of the area of this contour. So if I have fixed contour moving somehow, then torque is 0. Well, the odd viscosity dependent part is 0. It doesn't change with odd viscosity. But if I have expanding contour, then it is not 0. Okay, so there are simple three theorems. They all appeared before, but before they appeared more like in the Stokes flow, in approximation of flow velocity, some particular cases. But you can show this very, very generally in the... This is a very nice formula. Boundary conditions.
Which is made by hand.
So the way I'm thinking about it is that suppose that I have some solid shape which I change in time if I want, or move or expand or do whatever I want, and I put boundary conditions for fluid outside such that the velocity of the fluid particle on the surface equal exactly to the normal velocity of the surface. So equal exactly to the velocity of the point of the surface. This is no slip. So the fluid does not move relative to the surface at the surface. So this way, I basically take bulk, write this Navier-Stokes or those equations for vorticity and solve them with these boundary conditions, assuming that the motion of the shape is given. Okay. So these guys solved actually amazingly nice problem. There is a problem of swimmer in a viscous flow, what low Reynolds number. It's like bacteria swimming. So the question is, if you change the shape in a very viscous fluid, can you move? Can you propel without using inertia of the fluid, without using this jet type of motion? And the answer is yes, you can. And there is a gauge theory of these shape surfaces. There's very nice math there. What these guys did is they said, suppose we add odd viscosity. So what will change? And they derive this formula in particular case when this is very viscous flow and velocity is very small. But this formula is true under these conditions generally. Okay, so what I'm saying is that this is mostly like negative statements, except for maybe these small positive parts. That it's very hard to observe effects of odd viscosity on globally, on global things like total force. So these are a couple of examples. Let me more or less skip them, but one particular example is the Stokes problem. So which is motion of the ball, or in this particular case of circle in a viscous fluid. In 2 dimensions, it's very subtle on itself. There is a Stokes paradox, but it can be resolved within Navier-Stokes equation. And because it can be resolved and I can still use no-slip boundary conditions, I can immediately conclude that, for example, net force acting on this is 0. Net force depending on all viscosity is 0. So in particular, you might think that parity allows me to have lift force. Yeah. In 2 dimensions, the force is not 0, but odd viscosity part of the force, odd viscosity dependent part of the force, according to the previous slide, it should be 0. This is not obvious right away because you have broken parity, so you might expect that if you move it this way, then you will have some lift force moving to the left or to the right. It's allowed by symmetry. But the theorem...
In this case, the area doesn't change.
In this case, area doesn't change, so there is no torque as well. Yeah. Okay. And the question is how to observe effects of odd viscosity if it's so difficult according to the theorems. Well, the one, of course, easy case is to consider compressible systems, which already discussed by Avram. Another thing is to measure actual local forces and torques. So not the force acting on the whole shape, but the distribution of forces along the surface. It changes without viscosity, although probably harder to measure. And then you can take systems with boundary conditions which are not fully determined by the flow. For example, no stress boundary conditions. And examples of these conditions is air bubble. For example, if you have air bubble in the fluid, or 2-dimensional air bubble in the fluid, then the boundary condition should be that the force from outside should be equal to the pressure of the air from the inside, and pressure cannot be in tangent direction. So in particular, tangent force from outside should be 0.
But
Yeah.
if the surface moves, then there is no equilibrium between the forces.
There is if you assume that the mass of the surface itself is 0, then if you have slight difference between forces, the acceleration will be infinite if mass is 0. So of course, if you have film with a particular density of mass per unit area, then you have to include it into the equation. But let's assume that it's just the surface of the air bubble, so there is no actually mass there at the surface. Then the force inside should be the force outside, otherwise acceleration would be infinite. In any case, you have pressure here which is bigger than pressure here. Then there is net force on the unit area, but mass is 0. Acceleration is infinite. So not possible. So this is actually continuity of the stress is what it's called. So air bubble is one example. Another one is just the surface waves on the fluid, also example of such no stress boundary conditions. The boundary conditions are different. No stress means that I have to take the stress, the full stress, which has odd viscosity part, and put it 0. So in this case, boundary conditions do include odd viscosity explicitly. So I should expect some results. Okay. Not necessarily. This is example when volume is not constant, for example. So the simplest example which everybody can solve just in a couple of lines is expanding bubble. So let me take the circle, assume that it expands with some rate. Gamma is the rate of the change of the area. And then just ask what is the distribution of velocity outside so that there is no stress difference between pressure and outside fluid. And you will see that in addition to radial velocity, which follows from incompressibility, there is also the velocity in azimuthal direction, which is given by a similar formula, where this is a ratio of odd viscosity to the shear viscosity. Okay?
Did you assume something about how does it expand?
This particular formula with this particular coefficient is when it expands slowly. If it doesn't expand slowly, there will be modified formula, but still can be derived. It doesn't matter. This is just simple as that slide shows it. But what I assumed is that on the infinity somewhere, there is also expanding surface. If I think of finite systems, then it's incompressible, remember? So then when I expand this one, I should expand the other one. Or I should take another bubble here and compress this one, and then I will have circulation around one and opposite direction around the other. Well, anyways, this simple problem shows you that indeed, when you replace conditions by no stress, you do have observable consequence of odd viscosity. And another problem that we solved, actually, this is very... This is... It is stationary, yes, that's right, yeah. And this is assuming incompressibility, I'm looking for stationary solution. So I do not consider, for example, finite speed of sound, otherwise it will be... Yeah. Another problem which can actually, it's very nice to work on this because you just take all hydrodynamics papers, you take some problem, you say, what happens if I add odd viscosity? You add odd viscosity, and sometimes you can actually take the full solution out of that paper. This happens here. Richardson in '68 solves the problem of the following type. He considers the shear flow, the boundary conditions at infinity is flow in this direction and flow here in this direction, so it's a shear. Takes bubble of arbitrary shape and asks what is the stationary form. In some time it will become stationary. And he found that the stationary form is ellipse. And the parameters of this ellipse are given by in his case, viscosity and surface tension. With surface tension formula is quite complicated. Without surface tension, he had slit. He had really, this bubble would be infinitely stretched and will be like a segment. What happened here when we added odd viscosity, we basically repeat Richardson's equation and see that odd viscosity plays a role of surface tension in stabilizing the shape. So the equilibrium shape is ellipse with parameters, the angle of the slope of this ellipse is given by the ratio of the viscosity to even viscosity. Alpha is this angle, the angle of the slope of the ellipse to the x-axis. So if nu odd is 0, the alpha is 0 and it's a slit in this direction. It's just not ellipse but segment. And this rho is the ratio of major axis minus minor axis divided by major plus minor. Deformation of those. The ellipse is characterized by two things, except for the total size. One is the orientation of the ellipse. It's not eccentricity, it's the major axis minus minor divided by major plus minor. I think it's not quite eccentricity, but related, of course. So eccentricity can be expressed in terms of rho. So basically he solved it exactly, but what we see is that when nu odd is not 0, then it's actually ellipse, not a slit, even without surface tension. So nu odd plays a role of surface tension, and we sort of understand why. If you think about this sharp piece, then of course there will be bigger gradients of velocity here, and that means that the odd stress will create additional forces here, and that's exactly what surface tension would do. If you have this big curvature here, surface tension force will be bigger. So in a sense, it emulates surface tension. But my main point is that the following: you can solve this problem, and you find there is observable consequences of odd viscosity, which can be measured. So if I had this system, I would just look at the angle of the ellipse. I would tell what odd viscosity is. Say it again. In 68, he did the same, but without odd viscosity. Without odd viscosity. Odd viscosity was born in 95. So, but with surface tension, we also did with surface tension. There is some elliptic integral. The formula is a bit more complicated, but you can just borrow his solution. Actually, very interesting technical point is that you can just borrow his solution totally, except that instead of nu in his formulas, which is shear viscosity, use complex viscosity, which is nu even plus I times nu odd. So this odd viscosity is combined with regular viscosity in some complex number. You plug it in the Richardson equations, and then that gives you a solution. Okay. So I'm switching to the next topic. So I have 5 minutes, right? Okay. So these are my collaborators. This is Leiden group headed by Vincenzo Vitelli, and this paper is also recently out. It's about active rotors. So here I'm only showing pictures, no formulas. So there are systems which are very popular recently. It's a big interest in community. It's chiral active liquids, fluids, or chiral or active rotors. So activity in this context is a generation of angular momentum. So we can think, for example, about the system of molecular motors, which give particles some spin, or active colloids. So the experiments which William Irvine in the University of Chicago is conducting as the following: that he has some ferrofluid type colloids which have magnetic dipole moment per particle, and then he takes external magnetic field which he rotates in plane magnetic field, which he rotates in this plane with frequency of something like 9-10 hertz, and as a result, these fluid particles are rotating with constant angular frequency. And then he's studying motion of this fluid. He applies additional forces and looks how these fluids move. So in these fluids, the individual particles have non-zero angular momentum. So whenever fluid moves, it's also transport of angular momentum. That's the big difference. You can do driven grains, like of the system with this rattleback, which I showed. This is driven grains. And all these interesting features, which also people experiment with. This is something made out of plastic. So this consists of two parts. There are two holes here, and when you put it in on the surface and you put air from underneath through the small holes, then air comes in and gets out of this holes, and as a result, the torque is created. So these things rotate, and they put also some small magnets on top, so they interact as dipoles, also magnetic dipoles. They repel each other or attract each other, and they look how these things move when there are many of them. So as a result, there is some effective dynamics. Important part of this dynamics is that there is some exchange between internal rotation and orbital motion of the center of masses. For example, if you think about individual piece of this type as some kind of gear, and they collide in a central way, then because they rotate in the same direction, then as a result of the collision, they go a little bit sideways, and there is, you can see now that there is an angular momentum, orbital angular momentum relative to the center of mass. So there is some exchange between intrinsic rotation and external orbital angular momentum. However, because external torque is applied, then they of course lose a little bit of the intrinsic angular momentum, but that is restored immediately because force is continuously applied. So they will go back to the equilibrium value, which is given by dissipation of rotational motion and external torque applied. And but already part of it is transferred into orbital motion. So you can ask questions like, what is the stationary solution for motion of these objects, for their density, velocity, and so on and so forth. So these are important parts of this dynamics of active rotors. There's conservation of mass, momentum, and angular momentum, which is important here. There is additional degree of freedom, which is rotation. So you have to take into account additional conservation law. There is intrinsic angular momentum per particle. There is external torque constantly applied to the system, otherwise it will decay because of various dissipations. In quantum Hall effect, you don't need external torque because of the quantum physics, they rotate anyway without dissipating. There should be exchange between intrinsic and orbital angular momenta, and I explained how roughly it happens. And there is, of course, damping of all type of velocities in realistic system. And what we assumed in our work, which I advertised, is that odd viscosity dominates odd stress. Odd stress is actually this non-conservation of angular momentum, which comes from this mutual friction. We assume that it happens. We need this exchange, but we assume that it's small compared to the fact that each particle has non-zero angular momentum. So we're thinking that they rotate quick, and the velocity of rotation is almost constant. If you do that, you can integrate out or average over angular momentum degree of freedom and produce equations of motion containing only velocity and density, and that equations have odd viscosity in it, and that odd viscosity is precisely half of the intrinsic angular momentum. Okay, so we solve few problems with such a hydrodynamics. One is the famous solution called Oseen vortex. If you have fluid with dissipation, consider vortex solution, then you'll basically have distribution of velocity of this type, which will be actually, this vortex will be shrinking in time because of the dissipation, but you will rescale density. So there is explicit analytic solution. We added odd viscosity, solve it explicitly again, and we see that interesting phenomenon happens. So the subtle part is that we solve weakly compressible fluid. So we assume first that fluid is incompressible. We find velocity distribution. It does not change according to the theorems which I showed before. However, the vorticity is different in different points, so it means that actual pressure is modified. And therefore, if you assume now weak compressibility, it means that the density will slightly vary. You can do it consistently, so it's like two-step approach. And you will see that this is the solution for the density for absent odd viscosity. So there is the dip in density, which is like the dip in the eye of tornado, the low pressure in the eye of tornado. But then, if you add odd viscosity, one small one, you can have buildup of particles in the center of the vortex, or if you do it in the opposite direction, the effect is increased. Okay, and now I'm wrapping up. So the same in shocks in chiral fluids, we see that if you have a shock in x direction, there is also Vy component developed, the transverse motion which is developed due to the odd viscosity. Let me skip the details. If odd viscosity is bigger than regular velocity, there is dispersive shock waves. There's some interesting other things going on. And I'm summarizing, but this is one of the types of the summary which consists of many slides. So you think that, oh, it's not, finally it's over, but then we'll do the next slide. So be prepared. So we considered parity breaking in isotropic two-dimensional fluids, odd viscosity in compressible fluids as well. This is a particular consequence of parity breaking. So we made several exact statements for flow-dependent boundary conditions and few examples for no stress boundary conditions. And we saw that there are some observable consequences of hot viscosity, and we discussed some effects of hot viscosity in active rotor systems. Let me now give you this diagram, which is, I'm quite fascinated with these diagrams, and that particularly explains where quantum Hall effect is. Let me consider compressible fluid with rotational degree of freedom. That's a very general case. Then if I assume that this rotational velocity is of the same sign and is roughly constant, I can forget about this rotational motion, but I will get compressible fluid with odd viscosity. Okay? Then I have two ways to make it incompressible. One way is to say that it's actually incompressible, that divergence of velocity is zero. Or essentially, practically, you can take something like water and increase speed of sound and just say that it's very hard to compress. And that's incompressible fluid with odd viscosity, which I discussed in this talk. But you can do other things. You can take this fluid and say that by some reason, the vorticity of the fluid, the curl of velocity, is proportional to deviations of the pressure of the density from the background density. Let's just assume that. It turns out that this is important physics of quantum Hall effect. This is what happens in Hall effect. Remember, I said that Hall effect is something like condensation of particles coupled to vortices. In liquid helium, the condition is that curl of V equals zero. So there is, except for quantized vortices. So here it's proportional to particles. So it's like particles with vorticity condensed, not just vorticity. And this will result in a whole fluid with odd viscosity. And this is a little bit different problem than this one. So in this talk, I concentrated on this one. This one remains to be studied in this language. And finally, outlook. There are many applications, many systems which you can apply this to. And also nice thing for theorists is there are many hydrodynamics problems to solve. You take a book, you find the problem, you add odd viscosity. That's a new problem. You can try to solve it. Thank you very much. Right. If you have a surface, you have a gradient of velocity here. There will be additional force out of additional local surface on this surface in plane force. Yeah. Let's stick not with soft bubble, but let's take a solid surface, so that I still use no slip boundary conditions. Okay. Then I solve this problem. Solution will be for velocity will be exactly the same as without odd viscosity. But now I assume that this surface has some elastic properties. So which means that I'm able to measure local force. I will see it. Yes, out of plane. No, inside plane. But when I say surface, I mean line. I'm totally in two dimensions. So you can think about 3 dimensions and cylinder if you want in this way. But the force will be in plane force acting on the line, and line will buckle. So but if you take closed loop, then there will be increase here, decrease here, and as a result, if you sum up all forces, the theorem is that the net force will be 0. But it can be deformed still. Yeah. Yes. Yes. First of all, these terms, strictly speaking, are not topological. This omega depends on metric, so we will call topological terms which do not depend on metric at all. So it's kind of in between. It's very interesting. This omega the omega term, although you contract indices using epsilon only, no metric, but omega itself depends on metric. So therefore, there is metric dependence. Therefore, I am careful. I'm calling them geometric terms. As soon as you have parity breaking, you can have these terms in principle. The question is how to determine those coefficients. And in particular cases of pure quantum Hall states, we know these coefficients. My belief, this is not yet confirmed, but my belief is that they have different degree of universality. There is a gravitational Chern-Simons anomaly term. That coefficient should be universal because it's related to gravitational anomaly. But coefficient of those V and Z terms is related to the exact quantization of momentum transport. If you have impurities, the momentum conservation is broken. So I believe that in the presence of impurities will flow as RG, and for plaginar systems it will go to zero. But this I don't know. That's work in progress. About topological insulators, I'm not sure I have something to say. Yeah, so the problem is how is the momentum transported in those topological insulators. Because the insulators, it's usually people do not ask this question. Probably they might, yes. Which result? Sorry, just. So, if you have, the easiest way to explain it is this way. If you have quantum Hall effect, and if you assume that magnetic field has local maximum, but everything is smooth, but you put a bit more of magnetic field, then Landau level will have bigger capacity, so there will be more electrons in this particular region. Well, when you have rotating fluid, if you go, it looks like a increase of magnetic field, so you will have influx of electrons. So I always think about all this as very close to flat background, small velocities, density is almost constant. These are small deviations. If you have, this alpha can correspond to fractional Hall effect, but effect is still there. So it's 1/3, but still, no, it is not compressible. It's not compressible. Well, but incompressibility of different type. Look at this. Suppose that you want to compress this fluid, like you have a big system and you want to compress it. It means that you have to increase vorticity. It means you have to increase velocity, and the energy will diverge logarithmically with the size of the system. So this fluid is effectively incompressible at large distances anyway. But locally, you can change density by changing velocity. So I do not impose that divergence velocity is 0 or rho equals constant. In this sense, it's locally compressible. But if you call incompressibility the global incompressibility in thermodynamic sense, it is incompressible. No, local. The global means that if you take big system and apply pressure, that it will not change in size, in volume. Right? That's thermodynamic incompressibility. So this system is compressible, but thermodynamically incompressible. That's what I would say. Okay. It's from the point of view of hydrodynamics, it's different constraint. It is compressible. Yes, I agree. If you ask now, is it possible to actually compress the big system by some particular fraction? The answer is no, because the density, the energy required for that is logarithmically big with the size of the system. So thermodynamically, it's incompressible. Locally, it is compressible. It's like a plasma. So if you have neutralized background and you have plasma, then locally it's compressible, but that requires gap. That requires some dBi energy.
Questions? Let's speak again.